In our last video session addressing the adaptive immune response, we're going to discuss the concept of immunological memory and how that leads to the development of vaccines. Immunological memory is a cardinal feature of the immune response, and it's illustrated here. When we are infected with a pathogen, this can lead to rapid expansion of the pathogen, but it also leads to activation of T and B cells. These T and B cells are that are specific for the pathogen are present at low frequencies, but they undergo rapid clonal expansion and divide many times, and as they divide, they also develop important effector functions that allow them to clear and control the pathogen. But once the pathogen is gone, most of those effector lymphocytes die, leaving behind a long-lived population of memory T cells that are available to respond to a secondary challenge. Some key features of this response is that at memory time points, there's a higher frequency of T and B cells that are specific for these previously seen antigens. These memory B and T cells can get activated faster upon reactivation, and these memory populations can be very long-lived, in some cases even lifelong. Here's an example of how that works. A single exposure to an antigen may lead to a short-lived IgM response, but a single exposure with T cell help can lead to the formation of a more long-lived IgG response through the formation of long-lived plasma cells. A second exposure to an antigen, on the other hand, can dramatically boost the response by activating memory B cells, which can give rise to another round of long-lived plasma cells that continuously produce antibodies. Therefore, multiple exposures to an antigen boost the titers of antibodies, and they boost the affinity of antibodies, and each round of exposure boosts the number of memory B cells. Okay. So this is what this might look like in terms of an antibody response. This is the antibody levels after a primary, secondary, and tertiary boost. You can see that the response converts mostly to an IgG response, and the antibody levels increase with each boost. But what also happens is the antibody affinities increase with each boost, because with each boost, there is another germinal center reaction which drives another round of somatic hypermutation and affinity maturation within the germinal center. You can see this in the real world. This is an example of a study that was done in early 2021 after the introduction of the COVID-19 vaccine. This is a comparison of antibody titers in individuals that had either been previously exposed to COVID-19, seropositive, or individuals that had not been exposed to COVID-19 that were seronegative. And what we're looking at is the titers of antibodies at the given time points after the first vaccine and second vaccine dose. And you can see that prior exposure to these antigens led to a much stronger boost in the antibody response over time. And so this is just an illustration of how antibody responses are boosted after multiple exposures. Now, we have a number of vaccines that have shown dramatic efficacy in reducing disease burden. What I've shown here are a number of diseases with the maximum number of cases in the peak year and the number of cases in the year 2009. And I think you'll notice the dramatic drop in the number of cases in the United States for these vaccines. We do have a number of multi-drug resistant strains of pathogenic microorganisms that are arising, and more protective vaccines would be helpful in these cases. Vaccines can reduce disease burden. This is an example very early on of analysis of the COVID-19 vaccine, one of many studies that demonstrated a rapid decrease in hospitalization rates for those that had received the vaccine. This was true across all age groups. So what kind of vaccines do we need? Well, we need vaccines that can induce antibodies that can neutralize or opsonize or activate complement. We need vaccines that can induce T cell activation. We need vaccines that can provide protection. We need vaccines that ideally would disrupt transmission. However, this is difficult to achieve in the case of many respiratory pathogens. And so in that case, we want vaccines that can disrupt serious illness and death. We would like to generate vaccines that can protect from other sorts of diseases, such as protection from malignancies, or immunotherapeutic vaccines that can alter disease pathogenesis. And we really need vaccines that are safe and cheap and stable. What are some of the commonly used vaccine strategies? Well, the earliest strategies were live vaccines. This includes things like the smallpox vaccine, which is no longer used because smallpox has been eradicated. These live vaccines that we use now are generally attenuated versions of the pathogen. These attenuated pathogens have limited replication, and this includes things like the measles, mumps, rubella, polio, and varicella vaccines. We also commonly use killed vaccines. These are pathogens that have been chemically inactivated or fixed that are not able to replicate because they are dead. This includes the influenza and pertussis and rabies, and also another version of the polio vaccine. Some vaccines are subunit vaccines in which we vaccinate not with a pathogen, but with only a portion or piece of that pathogen. This includes proteins or polysaccharides derived from a pathogen, and this includes things like the hepatitis B vaccine, the Haemophilus influenza vaccine, the meningococcus vaccine, and the pneumococcus vaccine. It also includes vaccines that are specific not for the pathogen or even a component of the pathogen, but for a secreted molecule that is produced by the pathogen. And that is the case of toxoid vaccines, in which we generate antibodies to diphtheria toxin or tetanus toxin. Lastly, we have developed a new class of vaccines recently, and these are nucleic acid vaccines, mostly exemplified by the success of the RNA vaccines. These are ready-to-go RNA transcripts that are delivered in lipid nanoparticles. These are being used as COVID-19 vaccines, but are also prominently being studied as potential cancer vaccines. How do we get these vaccines to work? Well, especially in the case where we use a killed or subunit vaccine, we need something to help induce an inflammatory response so that we can generate a robust immune response to the vaccine. And that is where adjuvants come in. Adjuvants are products that induce an inflammatory response. The mechanisms are often poorly understood. This is an area that requires a lot more study. Alum is the most common adjuvant in humans. This is the current recommended vaccine schedule for children and adolescents 18 years and younger. I hope this does not change drastically over time. There have already been some changes to this vaccine schedule, but it will be important for you to familiarize yourself with the vaccines that are available and when they are available to different patients. There are a number of challenges that one should think about as we think about new vaccines. One is, what is the route of vaccination that is optimal? Should we inject vaccines? Should vaccines be inhaled? For example, the FluMist vaccine. What is the appropriate timing for a vaccine? Should vaccines be delivered immediately after birth? Should we wait a few months or a few years? That varies from vaccine to vaccine. What is the dosing schedule? How many boosts are optimal, and how far apart should those boosts be? We have to deal with the fact that many pathogens are highly polymorphic. Malaria is infamous for its ability to express many different antigens and thus evade current vaccine approaches. Some pathogens are also infamous for their ability to develop escape mutations, such that we are constantly having to develop new versions of the vaccine for things like influenza and COVID-19, or we are unable to develop vaccines at all, such as for things like HIV. And one of the tragedies of vaccination is poor vaccine distribution. Even now, with a very effective measles vaccine, there are over 100,000 deaths globally every year due to measles.